Hey, welcome.
Welcome to Lesson 9.3, Solving Rational Equations.
In today's lesson, we're going to take a look at methods that we can use for solving rational equations. It makes sense that we're here today at the end of Module 9 solving rational equations because we've looked at graphs, all kinds of graphs of rational functions, complicated ones, simple ones. We've added rational expressions, we've subtracted, multiplied, divide, and now we come to solving. Now, what exactly is a rational equation? Well, a rational equation is an equation that contains one or more rational expressions. The time t in hours it takes to travel d miles can be determined by using the equation t is equal to d over t. D over r. That is a rational equation. And in this case, the r is the rate of speed, the d is the distance, and of course t is the time. That's one type of rational equation we'll take a look at. Now, one of the methods we're going to look at for solving rational equations is graphing. So we're going to take a look at a more like a physical hand graphing method of solving it, also using our graphing calculator. So let's say we wanted to solve the rational equation x over x minus 3 equals 2. And we wanted to solve by graphing. We could go ahead and take a look at all the features that we know about this graph, and we could construct a graph of x over x minus 3. And then, of course, we could then also construct a graph of y equals 2, which of course is a horizontal line. And we could look to see where the two would cross, and that would represent the solution if there was one. So taking a look at x over x minus 3, so we know the features we want to look for are things like vertical asymptotes. So we're going to see if there's vertical asymptotes. We're going to look for horizontal asymptotes. We're going to look to see if there's a slant asymptote, which I can tell in this case there's not because the power on the top is not higher than the power on the bottom. We can look to see what are the x-intercepts if there are any, see if there's any holes. This is a pretty simple graph, and so I can see that there is a vertical asymptote. That vertical asymptote is going to be where the denominator is 0, so that's at x equals 3. So we know we have a vertical asymptote right here at x equals 3. Now, unfortunately, this graph is scaled by 2, but we have a vertical asymptote right here at 3. Well, it looks just about at 3, I guess. So at x equals 3, we are going to have a horizontal asymptote. Remember that if the powers on the top and the bottom are the same, we just simply divide the coefficients on the highest power, which in this case, there's the coefficient on each is 1, so 1 divided by 1 is 1. So my horizontal asymptote would be at y equals 1. I also could have used long division to divide x by x minus 3 and put that in that standard form. This is going to be a hyperbola. So at y equals 1, so right about here, between 0 and 2, I've got my horizontal asymptote at y equals 1. I can tell that this is going to actually cross the x-axis one place. It's going to be where the numerator is equal to 0, and that's at 0 itself. So I have an x-intercept at x equals 0. So this is going to cross right here on the graph at the origin. And other than that, I can use this table over here to create a graph, or I can simply use this and fill in this table. So I have a table with some selected input values. So I'm just going to go ahead and substitute those in. When I substituted in 0 into that left side of the function here, I'm going to plug them into this side. I got 0 out, so my ordered pair is 0, 0. When I plugged 1 in, I got negative 1/2. When I substituted 2 in, I got negative 2. When I substituted 4 in, I got 4. I put 5 in, and I got 2.5, or 5/2. And when I substituted 9 in, I got 1.5, or 3/2. And I'm going to go ahead and plot these points over here. So I have a point 0, 0, which I can see is already on there. That was the x-intercept. I have one at 1 and negative 1/2. So let's see, go over a 1 and down a 1/2. maybe right about in there. Yeah, that looks about right there. I have 2 and negative 2, so over 2 and down 2, that's going to put me right here. And that actually kind of gives me an idea of what that branch looks like, because with the asymptotes I can pretty much sketch. Now let's fix that. I can sketch it looking like that. Then on the other side I have some points, so if I substitute 4 in, I get 4 out. So over 4 up 4, that's going to put me right about here. I have 5 and 2.5, so over 5 and up 2.5. So there's 2, and there's just a little above that. Well, it's about right there, maybe. And then finally 9 and 1.5. Over 9, up 1.5. That's going to put me just a little above that asymptote. And so that I can see this graph looks like, this branch of the graph looks like this. So that's the left-hand side. Now the right-hand side is the equation y equals 2. And so y equals 2 is just a horizontal line right through 2, and that's going to put me right here. That's the line. Y equals 2, just above that asymptote. And I can see pretty clearly that this graph is going to cross. Let's see if I can change the color here. This graph is going to cross right about here. And that's where that solution is going to be. Now, if I had to estimate it, it looks like, and I don't think I did a very good job of it, obviously, because it's not the correct answer, but it kind of looks like it's crossing maybe right, yeah, that's probably a little closer to where it's at right there. Right there. And that looks to me like it's crossing when x is 6. So maybe I would want to use my graphing calculator to be sure, or I could actually plug in 6 into that function and see if it turns out. And in fact, that's what I'm going to do, is manually check it. So if I plug 6, make x be 6, I'd put it into that function, 6 over 6 minus 3. And I'm going to put that right into this equation right here. And 6 over 6 minus 3 is 6 over 3, which is 2. So 2 equals 2, and so that checks. So my solution is x is equal to 6. Now I also did it on the graphing calculator, and I'll show you what that looks like. So taking a look at the graphing calculator method, I just simply substituted in each side of that equation into y1 and y2. As you can see, I did that here. I graphed it, and you can see a graph that looks very much like, in fact, even matches the colors of my graph. I kind of did that on purpose. And I can see that spot on the graph right there where those cross. And I looked in the table, and it just so happened, because this was a nice integer value, I was able to see that solution right there in the table right here at 6, and the output is 2 for both. So that's the value where they're the same. That's the solution. Now, if that had not been an integer value, I maybe would have used the second and calculate intersection function key and just saw where those two graphs crossed. So those are all valid methods using graphing. Now, I tend to trust the algebraic methods a little bit more, just because, you know, graphing is a little bit limited unless you do use that calculate intersection function. Then you could, you know, estimate if it wasn't a nice integer value. But we're going to take a look next at using algebraic methods. Now, one of my problems with rational equations really is just that they're, at the end of the day, they're fractions, right? And you know, fractions are kind of quirky. They have so many rules and things and how they work, and so usually if I can, the very first thing that I do is try to just get rid of all the fractions. Well, how does that happen? Well, it turns out that if you just simply multiply every term in the equation by whatever would the LCD or what the common denominator would have been, if you multiply each term by that LCD, it should clear out all of the denominators and just turn it into a polynomial equation. That means it could be a cubic one, it could be quadratic, it could be linear, whatever. So now, one of the things we have to be cautious about is that this eliminates the information about the excluded values of the original equation, and so sometimes that could produce a solution that in fact doesn't really work back in the original equation. It's a solution to the polynomial equation that we're actually solving, but when you go to put it back in the rational equation, the original equation, it doesn't work, and that's called an extraneous solution. So that would be a solution that algebraically seems to work, but when you do substitute back into the original, it does not produce a solution that works. Like it might make the denominator equal to 0, something like that. And so we always have to be on the lookout for that. So let's go ahead and see if we can first figure out, so the goal is always originally, first step is to figure out what the LCD would be. So in other words, what the common denominator would have been for these fractions. Well, I can see my two fractions are, well, one of them needs to be simplified. One's written as 2x minus 10, so if I factor it, I could take out that 2, and I could write it as 2 times x minus 5. And so looking at those two denominators, I can clearly see that the LCD would be 2 times x minus 5. That way it would include the x minus 5 in the left-hand side and also the 2 that's on the right-hand side. So what I'm going to do is I'm going to take each one of these terms. I'm going to actually rewrite this. This helps a little bit to stay organized. And I'm going to rewrite, and next to each one of them, I'm going to multiply by 2 times x minus 5. Oops. And so the left-hand side I'm going to multiply by that. So here's the left side, and then on the right side, I'm going to write the 5x plus 17 over the 2x minus 10, or 2 times x minus 5 in factored form. And then again, I'm going to multiply that by the 2 times x minus 5 over 1. And the reason why I can do that is because of the multiplication property of equality. Remember, you can, as long as you do the same thing to both sides of the equation, you're not changing it at all. So as long as I'm doing it to every single term, then this is still equivalent. So now you can see that I have an x minus 5 here on the left-hand side that can cancel out with that x minus 5. And what's remaining now is 2 times 3x plus 7, which is 6x plus 14. And then on the right-hand side, I can see that I have the x minus 5 that cancels, also the 2's that cancel, and I'm left now with 5x plus 17, and that's quite an easy linear equation to solve then from there. So you just have to get variables on one side, real numbers on the other. So I could subtract 5x from both sides, leaving me with x here. I could subtract 14 from both sides, leaving me with 3 here. So I got a value for my solution of x equals 3.
So now we talked about this idea of an extraneous solution and how we would know if this value that we got, x is 3, is an extraneous solution. It's really just to go back to the original equation and substitute it back in. Now, you really only, as long as your algebra is all correct, you really just need to substitute back into the denominators and just make sure it doesn't make any of the denominators equal to 0, because that's where those excluded values occur, right? Is where those denominators would have a value of 0. So I can see that the only value I really need to be concerned with is if I had gotten x was 5, then that means that one wouldn't have worked back in the original, but I got x equals 3, so we're going to go with that solution, x is equal to 3. Let's turn the page and look at another example. All right, so now this time, it's a little more complicated equation. We have two rational expressions on one side that are being added, and then on the other side we have a rational expression as well. And so you might think that maybe, oh, we're going to have to add rational expressions, we're going to have to add those together, but we don't. Remember, we said that as long as we follow this strategy of multiplying every term by the LCM, actually technically I do the LCM or LCD over 1, then if we do that, we should be able to clear out all of the fractions and turn it into a polynomial equation. And so kind of taking a look at what the LCD, or the least common multiple of the denominators, is, you can see that we have a x minus 7, and there's another x minus 7, and then there's a 2. And so we just have to make sure that each one of those denominators is represented. And so to do that, we could just simply multiply by 2 times x minus 7. And that way we've covered all the different possible denominators. So I'm going to go ahead and rewrite this equation, and in front of each one of those factors I'm going to put 2 times x minus 7 over 1. I'm going to multiply each one of the 3 separate terms by that factor. So I'm going to take a second and I'll just rewrite it, and you can do that as well. Just take up a little bit of space as you have to kind of rewrite everything with an extra term in front. Okay, sorry, I got interrupted by the announcements. So anyway, I'm going to go ahead and rewrite this. So I'm going to take every one of these terms here, and in front of it I'm going to put this factor, this 2 times x minus 7 over 1, and I'm going to just multiply each one of these terms by that factor, which is, again, the LCD, or the least common denominator. It's the least common multiple of the denominator, in other words. And I'm just going to take a second and write each one of these. So again, between each term, and again, terms are divided up, separated by addition, subtractions, equal signs. But in front of each one of these terms, I'm going to put, so it takes a lot of space, put this factor in there. Sometimes I think it helps to kind of like separate it off so you can see that this is the part that you're adding to the equation. And then got another 2 times 7 over 1, and then that takes a little bit of time to do that. But there's a big payoff here, because now we're going to get all of these denominators to just cancel out, and we'll have a polynomial equation. So I'm going to go through and cancel out of this first term. I'm going to get rid of those x minus 7s. What's left over then is this 2 that I have to multiply by this 2x minus 9, which is 4x minus 18. And then out of the next term, I'm going to be able to just cancel out the 2's, and that leaves me with an x times x minus 7. So distributing the x through would give me x squared minus 7x. And on the other side then, the x minus 7's will cancel out. All that's left is the 2 and the 5. 2 times 5 is 10. And so this turns out to be a quadratic equation, and so we know that if we have a quadratic equation, our strategy is to get everything on the same side, and hopefully we can factor it. So grouping everything on the same side, I'll just bring that 10 over, put it in descending order of powers, and put my like terms together. Let's see, I have x squared, there's that. I have a negative 7x and a positive 4x, that makes negative 3x. I have a negative 18, and I'm about to bring a negative 10 over. That makes that minus 28. And then to solve, I'm just simply going to factor and kind of run a little bit out of space. But factor, I have an x, let's see, 2 factors that multiply to negative 28 that add to 3. So that's going to be a 7 and a 4, with the 7 being negative, so negative 7 and x plus 4. And that means my 2 potential solutions then are what make these 0. So x could equal 7, and x also could equal negative 4. Now we want to make sure that they don't cause a problem with our numerators, our denominators. And so taking a look at that 7 right there, if I were to put that in back into the original, you can see how it would make those 2 denominators 0. And so I just simply have to x that one out. I can't count that as a valid solution, and that just leaves me then with x is equal to negative 4, because that negative 4 does not cause any problems with those denominators, and that gives me one solution, x equals negative 4. So we're going to go ahead and designate this next one as a U-try question that we will follow up on in class. So we'll have you pause the video now, give that one a try, and we'll just reveal the answer when I see you in class. So that way it gives us a little bit of time in this lesson video to move on and look at one more question together. We'll look at one of these modeling with real-world problems. So this next problem will probably seem very familiar. We looked at some problems like this in the prior module, although the equations had been written for us. And so I mentioned then that at some point we were going to have to write these ourselves, and so here's that time. So we're going to use a rational equation to solve this problem. Kelsey is kayaking on a river. she travels 5 miles upstream and 5 miles downstream in a total of 6 hours. In still water, Kelsey can travel at an average speed of 3 miles per hour. So in other words, if there's no current or anything that is affecting, like pushing against her or with her, she can paddle 3 miles per hour. What is the average speed of the river's current? So I've created this table that's going to kind of help us come up with all the pertinent information here that we need to write our equation, and then now we know how to solve a rational equation, so we'll go ahead and use our strategies there. But the first thing is the distance. So it said that she travels 5 miles upstream and 5 miles downstream. And so I went ahead and filled in upstream and downstream distance of 5 miles. Now the average speed is going to be what she can paddle at, which is 3. But then when you're going upstream and there's current, that's working against you. So that's going to be reduced by whatever that current speed is. So that would be 3 miles per hour minus c, which c is a certain miles per hour that the current is traveling at. Now downstream, that means you're getting the help of the current. Like when you're going downstream, you're actually going to be going faster than what you can actually paddle because then the current's kind of helping you along. And so her speed is 3 miles per hour that she can paddle, but she's getting the benefit of adding that current to her speed. Now we know that distance is equal to the rate divided by the time, but since we want the time, we actually want to use the other version of that equation, which is, oops, I'm sorry, I just wrote that wrong. I meant the distance equals the rate times the time. I don't know what I was just writing, sorry. My fault. But we want to find the time, so we want to use the version of it that's solved for time, which is time is equal to the distance, distance divided by the rate. And so when we write this equation for our time, we take our distance, which is 5, and we're going to divide by our rate, which in the case of the upstream is 3 minus c, and downstream is the 3 plus c. Now you may remember back to those problems we were looking at in that prior module, and this is the format that we saw them written in, and we kind of really at that time didn't really think too much about where those equations came from. So we want to find out what c is, this average speed of the current, and so we have to write an equation, and we know that if we look at the two trips, the upstream and downstream trip together, this would be an addition problem that would look like this. And we know that that should actually equal the total time, which we can see here is 6 hours. So that's 6 hours right here. We're in a total of 6 hours. And it was a combination of the upstream and downstream trips. So that's an equation that we can solve using these strategies we've been talking about. So what we can do now is figure out what would be the least common multiple of the denominators. And so the LCD, or the least common denominator, would be the product of these two denominators, because they're, they look like they have something common, but really they're completely different terms. One's 3 minus c and the other is 3 plus c. So we're going to use the product of those two. So we'll use 3 minus c and 3 plus c. And we'll simply take every term and multiply it by that over 1. So I'm going to go ahead and rewrite with this in front of each one of these terms. So 3 minus c. I mean, you'll figure out eventually there's a shortcut to doing this, so you don't have to do this for every single problem. But over 1, and oops, I'm going to do this over 1, and I'll change the color, keep it a little more organized. For the actual original equation, I'll do them blue, and these things I'm going to add to my equation in order to cancel out the denominators, I'll do in red. So 3 minus c times 3 plus c over 1, and then going to multiply that by the next term, which is 5 over 3 plus c, and then of course on the other side as well. So 3 minus c, 3 plus c over 1, and then times 6. So, which is really 6 over 1. Okay, so here's where the magic happens. We get all these denominators to cancel out. So in this first term I see a 3 minus c and a 3 minus c. Those are going to cancel out. And what's left over is going to be the product of these two things, and that's going to be 15 plus 5c. That's what I get from that. And the next one, I've got a 3 plus c that's going to cancel out, and that one's going to leave me with, when I multiply the 5 through to both of these, I'll have a 15 minus 5c. And then on the other side, I don't really get anything to cancel out. So what's left are going to be these things that I'll have to multiply, which means I'll have to FOIL the two binomials, and then whatever I get multiplied by 6. So that's going to be 6 times, and when I FOIL the 3 minus c and the 3 plus c, I get 9 minus, and then you remember the insides and outsides of these are going to cancel because these are two binomials that only differ by the sign. So I'll have 9 minus c squared. And I can now go ahead and simplify everything. So on the left-hand side, this is going to simplify down. Now the c's cancel out, so that makes it convenient. 15 and 15 is 30. On the other side, I could distribute that 6 through. That makes 6 times 9 is 54, minus 6c squared. Probably the easiest thing for me to do here is to use the square root property to solve. I'm just going to subtract 54, and that's going to leave me with a negative 24 equals negative 6c squared. Divide both sides by negative 6, and that's going to leave me with a 4 is equal to c squared. And taking the square root, of course, of that is going to leave me with two possibilities. C could equal 2 or C could equal negative 2, but we know that the negative 2 doesn't really make sense because we're talking about speed of the current, and so that means C is equal to 2. Now, if you recall, when we did this in the prior module, the method that we used was by graphing. So we would graph them in our calculator, see where the horizontal line at y equals 6 would cross the rational function, that is the sum of these two upstream and downstream times. And but this is an algebraic way, which I really feel like we're at a point now, after just studying solving rational equations, that we can solve these algebraically. So that would be the expectation now, is we're going to use algebraic methods to solve this type of problem. And I think to wrap things up, we're just going to plan on doing this last example in class. So really, all you're going to need to do is make sure you've tried the you try question and taken your notes. So we'll see you in class.